Hey guys, welcome back. Well, it's been a minute since I did a video, but I thought I'd follow up from my last video where I introduced the Celestron Dew Heater Ring. I had just bought it and had been using it on a couple of nights and found that it was very effective at preventing dew. However, some of you wrote back and said, well, a lot of people have the same Dew Heater Ring and are seeing distortions of stars because of the heat in the corrector plate not being uniformly distributed throughout the corrector plate. So I thought I'd take a look at that and take a closer look at my images to see if I could see any of those effects that you guys are commenting on. So let's get started. In that last video, I presented some results where I had measured the temperature across the diameter of the corrector plate for 4 different power levels, 25%, 50%, 75, and 100% power level applied to the Dew heater ring. And as you might expect, I'm seeing a higher temperature out where the heat is applied around the outer perimeter, and that heat drops off as you get closer to the secondary mirror. And these are the results I got. If you take a close look at the 100% power level, I'm seeing, roughly speaking, about a delta T of 10 degrees C from the outer perimeter to the area in the corrector plate close to the secondary mirror. So what we want to do here is to see if this 10-degree variation in temperature is introducing any distortion into our images. Let's imagine we have a uniform thickness corrector plate. In reality, the corrector plate is not a uniform thickness. It is, in fact, a lens. In our case, the Dew heater ring is on the outside, out near the outer periphery, and it generates heat, and that heat enters the glass and then diffuses through the glass over a period of time until it reaches some sort of steady state distribution of heat through the glass. There are several things that can happen when you heat up the glass. One of them is just an expansion of material. All materials expand when heated. There is a coefficient called the coefficient of thermal expansion. Multiply that times the change in temperature, delta T. We're interested in about 10 degrees C here. And then multiply the alpha delta T times the original thickness. And that's how thick the heated glass would be. So there's a slight, very small increase in the thickness of the corrector plate just due to heating. Now, of course, in our case, the heat is applied up at the top here, and then it gets less and less. The temperature of the glass reduces as we go farther down on this page. So this line is not a constant. It's more sloped or curved as it goes down to the corrector plate. Another effect, which is very important and I am not considering here, is what happens when you have a thermal gradient across the width, meaning what happens if it's a bit cooler on the outside than on the inside. For example, this heat's going to come in, and then as it diffuses through, this glass here is exposed to cooler air. You will tend to have some radiation heat loss on this surface. On this other surface, you were shielded inside the tube of the OTA, and now that heat loss, that radiated heat loss is less. So I might expect as we get farther from this heat source up here, as we move down closer to the secondary mirror, you might start to see warmer temperatures here on this inner face than you see on the outer face. And a thermal gradient will cause out of plane warping and bending of the corrector plate. That's a very difficult problem, especially when you take the now warped shape of the corrector plate and then try to understand optically what happened to the light as it went through there and how it ends up on your sensor. I am going to take a look at the refraction of light through the corrector plate. In this case, the refractive index of glass is about 1.5. The refractive index of air is about 1. And so because we're going from a medium with a value of 1 to a medium with a value of about 1.5, the path that a light ray would follow enters the glass at some angle theta and then gets bent towards the normal to the glass, and then when it exits the glass, it returns back to its original path that it was on before it entered the glass. But there is a shift here. Where the light exits the back end of the corrector plate is going to be at a different location from where it would have exited had it come out and not been refracted. Refraction can change with the temperature. As the optical density of a medium increases or decreases, it affects the speed of light passing through that medium, and that changes the refractive index of the material at different temperatures. So what happens when you have a colder area of the glass, a lower temperature, the light ray might come out over here. However, in the hotter part of the corrector plate, that light will be refracted more, and so there will be a delta here. And now the question is, what does this difference here translate into when it gets back to our sensor? Where does the light exiting the cooler part of our corrector plate land on our sensor as compared to where does the light land that passes through the warmer part of the corrector plate? How much of a difference between the hot and cold refractive indices do we need to have before we actually see an H that's on par with what our pixel size is, which is about 3.8 micrometers. And in our case, we'll be looking at a delta T of 10 degrees. And if we assume that our cold refractive index is 1.5, then we need an increase of about 0.09. In other words, we need that hot refractive index to be 1.59 in order for the separation between hot and cold light getting to our sensor is on par with the size of a pixel in our camera sensors. Now, I looked and looked for examples of the kind of glass that we might have in our corrector plate and the variation of refractive index with temperature, and I swear I couldn't find it. What I did find is this analysis of light passing through the Corning 7980 prisms. And what you're seeing here is, in fact, the effect that we're talking about. We have temperature down here in Kelvin. Kelvin is just the Celsius plus an offset. So 10 degrees, a 10-degree shift in Kelvin is a 10-degree shift in Celsius. From very cold to pretty warm, a measure of the refractive index through these fused silica prisms at different temperatures. And that's what we're interested in. For us, we're up here around 20 degrees Celsius, and we're interested in a 10-degree shift. So what we're interested in is the change in refractive index. That's this distance here over a 10-degree width here. So if we have the refractive index at this value, we can simply use the slope of the line here, which is 1 times 10 to the minus 5 per degree Celsius, and multiply that times our delta T, and that gives us an estimate of what we expect the refractive index to be at that warmer temperature. We plug in the value of 1.4574 at 20 degrees C, then add on the slope here times the temperature difference that we're interested in, which is 10 degrees C, and that gives us 1.4575. We're only seeing a 0.0001 shift in the refractive index for these prisms for a 10-degree change in temperature. That's nothing close to the 0.09 shift that we're actually looking for. For the glass that we probably have, or something close to it, I found this reference, and we find that the shot N-BK7 is kind of a glass that's probably fairly close to what's being used in the corrector plate. It has an index of refraction of 1.5168. We start with that refractive index at 20 degrees. What is that going to be at 30 degrees when we get to the outer perimeter of the corrector plate? In this reference, they do provide that slope value, the dN/dt that I was referring to on the previous slide. And we'll just go up from 20 degrees C, get to this line, which corresponds to the green wavelength of light. And we come over, and it's about 1.5 times 10 to the minus 6. For the fused silica we were just looking at, that was 1 times 10 to the minus 5. That means the index of refraction is even less sensitive to temperature than it was for the fused silica. With a 10-degree increase in temperature, we're only getting 0.000015 shift in the index of refraction for glass, and nowhere near the 0.09 we need to get refracted light to end up in a different pixel due to the differential heating of the corrector plate. Now I have two pictures here. One was taken with the Dew strap in service at 100%, and one of the pictures was taken with the Dew Heater Ring also operating at 100%. You can see some misshapen stars. That's in part because of the focal reducer I'm using and not having the right back focus, or the focal reducer is just not that good. It's the Celestron focal reducer corrector for the SETs, and it does not have a great reputation. Another thing you'll see here is that if you look in this picture over here, the slope of the star is this way, and over here the slope of the star is this way. The camera for the picture on the right was rotated a bit, and so when I registered these two images, there is a rotation for the image on the right that is not present for the image on the left. And that's why you see a rotation. So forget about that. Just take a look at it, the shape of the star here, the shape of the star, the shape of the star, and then compare it to the corresponding stars in the other image. Do you see a difference? And the image on the left is the dew strap. The image on the right is the dew ring, but it was taken 13 nights later, which means we have a different moon brightness situation. We certainly have different seeing conditions, and we may have different wind conditions. So there are going to be other effects that are going to affect star shape. And you may say, well, I can see some differences. So let's zoom out to Still a very close-up view of the stars, and you can see here that this is M101. This is taken before the supernova was detected, about 2 days before, and this was taken after the supernova was detected about 13 nights later. So now if you compare star for star in the image on the left and the image on the right, one with the dew strap, one with the dew ring, can you see any differences in the star shapes? And again, we're still very much zoomed in even here. I would say that it's very difficult, if not frankly impossible, to associate any differences to the extent that you can even discern a difference between star shapes for the image on the left and the image on the right. From a practical point of view, I think it's impossible to tell the difference between these two images. As we've hinted at, there are other factors that influence the shape of stars. First of all, there's RA tracking. I've got the EQ6R. I love the mount, but it does not have encoders on both axes, and as a result, you are getting some effect of the uncorrected or the residual periodic error that's in the mount. Even though I've got PhD2 running, even though I've got a PET curve defined, you still can't get rid of all the periodic error. You're going to have some residual left, and that residual translates into elongated stars along the RA axis. So I've got that effect that's affecting the star shape. I've got deck backlash. Now, it's a lot less with my EQ6R than it was with my CGEM, but for some of you, the deck backlash is a big player and will certainly affect star shapes as well. Naturally, you've got seeing from night to night that tends to affect the star shape. There are clouds that pass through. And of course, there's the optical terrain. I'm using the Celestron focal reducer corrector with my SCT. It's not that great. It's certainly not fine tuned. I'm going to have to work on that, but that's a big effect on the stars out in the outer periphery. In my case, I've got them kind of tangentially stretched relative to the optical axis. And of course, there are guiding issues. The target elevation angle will certainly affect the size of stars as the target gets to lower altitudes. You're looking through more atmosphere. And of course, focus shifts throughout the night. And finally, at the top of this pile of grief, we have now the Dew Heater Ring, and maybe it's contributing something to the shape of the star as well. Is it truly possible to separate out the Dew Heater Ring effect, and I suspect there is one, versus all these other things that are going on? My objective here was to go back and take a look at the images I've taken with the Dew Heater Ring and with the Dew Strap and see if I could see some of the star deformation issues a lot of people are talking about who have been using this Dew Heater Ring. It is certainly plausible. Temperature variation will affect the plate shape and its refractive characteristics and its thickness, and those things can affect and redirect light to different areas of our sensor where we had not intended. But the question is how much? After all, if all the light that's affected by these thermal effects stays within 1 pixel width, then we're not going to see it. And frankly, if it's even outside 1 pixel width at a practical viewing distance for a photograph, you're not going to see it. I see about a delta T of 10 degrees C from the outer perimeter of the corrector plate to the perimeter of the secondary mirror. So that's kind of what I base my assessment on here is the delta T across the radially across the glass of a 10 degrees C. Based on my rough evaluation of thermal expansion effect on the thickness and the change in the refractive index with temperature, it certainly appears that these factors are not and could not be the cause of any star or image distortion. The refractive index of light just doesn't change that much for a small 10 degrees C change in temperature. I'm not seeing a diverted light path that would be larger than the size of a pixel back at our sensor. It's very challenging to take two images and compare them and look for differences. You will always see differences. And when you consider the number of factors that are affecting what stars look like in our images, it is very difficult. And indeed, when I compared a couple of images in this study, I can't see a thing. I can't see any obvious distortions that I would point to and say, yes, that's definitely due to variation in heating across the plate. Having said that, I'm not willing to say that those who were seeing effects are crazy. It's entirely possible and that there is an effect. It's just that that effect may be very small, and in my case, it may be buried in other stuff that's going on. Those people who are seeing issues with the Dew Heater Ring, it may be because they've got a well-tuned optical train, they've got a high-end mount, and they've got excellent seeing. If you wipe those things off the map, then yeah, maybe there is some effect that I'm just not seeing and can't see with my setup. If the Dew Ring is causing distortions that people are talking about, I suspect it's thermal-induced bending. In other words, a heat or thermal gradient across the thickness of the glass that is causing the glass to bend a little bit, and that is changing where the light is ending up on the camera sensor. For me, all the math aside, I'm looking at the images and they don't look that different to me. Reconsidering my dew heater conclusions from my original video, it certainly solves the dew issue. I think it's very effective at that. And I don't see any image distortion in my images, but I am admittedly not a star-shaped pixel peeper. Okay, guys, well, thanks for watching, and I'll try to get videos out in a more regular pace than I have been, and I'll check in with you later. See ya.